Hi everyone. In this video we are discussing problem number 19. Remove nth node from end of list. It's a problem from Leetcode. So let's read the problem statement. We are given the head of a linked list and our aim is to remove the nth node from the end of the list and return the head of the new linked list where just that one particular node is missing. So they have given some examples. So check this example number 1. We have this linked list containing 5 nodes. So the node values are, as you can clearly see, the numbers ranging from 1, 2, 3, 4, 5. And n value is given, kind of like the target value. Not exactly the target value, the target location is given. Okay, n is equal to 2. In the sense, we will have to remove the second node from the right, from the end, right? So from the end of the list, the second node is this node whose value is 4, and our aim is to remove that. So we have to remove this node, which means you will have to first unlink that link between 3 and 4. Also, we have to unlink the link between 4 and 5 and form a new link between 3 and 5. And this is our new linked list. And the head of the new linked list is the same node 1, but technically it's a different linked list. Since even if one node is different, it's considered to be a different linked list. Let's check example number 2. It's given that head is 1. In this linked list, there is only one node. So that is obviously the head node, and that is the only node that is given. And we are asked to remove the first node from the end. The starting and ending of this list is the same node. So if you're removing that first node from the end, it's like just removing that only existing node, and we expect to get a empty linked list. So we will have to return none here, right? And in the third example, we have a linked list of length 2, right? The head node is 1 and the next one is 2. And here n is 1. This is like the target location from the end. So we will have to remove the first node from the end. So you will have to remove this, the node whose value is 2, and we are left with just this head node. Right? So these are some of the examples. Now, let's head over to whiteboard and try to solve this problem. So let me give you a different example. Apart from the ones that are given in Leetcode, let me give you a slightly longer linked list so that we can understand what's going on. Okay? And I'm going to give very simple values, consecutive natural numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And this is a linked list. So imagine n value is given to be, say, 3. So what does it mean? From the end of this linked list, we will have to remove the third element, which is 1, 2, 3. This particular node we will have to remove. From the end of the list, we will have to remove the third node. This node we will have to remove, which means that we will have to unlink this link between 6 and 7 and unlink this link between 7 and 8, and we will have to just completely remove this node itself and form a new link between 6 and 8. So like I told you, this is counted as a new linked list, and the head did not change. The head of the list is same node, but it can change depending on what this n value is. Right? Here it did not change, but for a different value of n, it may happen so that we will have to remove the very first node itself. So we should also take into consideration that possibility that sometimes we may have to even remove the head node itself. Okay, fine. Let's go back to the original list. Okay, so this is the list given. This is the target location from the end. Okay, so what kind of approach we can take to solve this problem? One obvious approach we can take is we can have a separate array where we collect all these nodes exactly in the same order, right? We collect all these nodes exactly in the same order. So we get a new array. In that particular array, we can target the nth node from the right. Okay, and we can remove that particular node. And like I told you, we will form a new link between the previous node and the next node, right? So that is one way of doing it, but that is not a very smart way of solving the problem, because basically we are solving this with the help of a list, a separate list, a new list. Is there any way we can solve this problem in place? And also there is another challenging thing in this particular problem. We do not know how many numbers or how many nodes are there in this particular list. We have no idea. Listen, now we have the diagram of the entire linked list, so that we know how many nodes are there. Otherwise, usually we'll be given only the head of the linked list. Just by looking at the head of the linked list, we will not know how far the list will go, right? So we cannot do that basic arithmetic. Okay, I will take the number of nodes and then subtract it by the target node. It doesn't work like that. Okay, we have no idea how many nodes are there unless we traverse through this entire list. Okay, so even that approach we cannot take. So there is a much better way of solving this problem without forming a separate array where we collect all the nodes and unlink them and link them, or without doing this, finding out the number of nodes and then subtracting the target node, without taking any of these approaches. There is a much better way of solving this problem, that is the two-pointer approach. And it works like this. Let this green be the first pointer and this red be the second pointer. So we have these green and red pointers. Okay, let the green one be the left pointer and the red one be the second pointer, the right pointer. So with the help of these two pointers, there is a much better way of finding out which is the nth node from the right? Without going back and forth. Even if we want to, we cannot that easily go back. We can go forward, we can move forward, but we cannot that easily go back. I'm not saying it's impossible, it's not that easy to go back because linked lists are unidirectional. Okay, so without going back and forth, is there any way to find out the nth node from the right? We can do it by using this particular technique. The first thing that we're going to do is to run this right node n-1 times to the right. I repeat, we are going to run this right node n-1 times to the right. If n is the node that you're trying to find from the right, from the end. Okay, for example, I'll just keep it simple. I'll give you one specific numerical value. Let's say n is 4 this time. In that case, I'm going to run this right pointer n-1 times to the right, in the sense 3 times to the right. Okay, so right pointer will go to the next node, so count as 1, moving to its next node, count it as 2, move it to its next node, count it as 3. So now the entire length of the portion of this linked list ranging from the left pointer to the right pointer is equal to 4. If you run it 3 times, only then the entire length of this portion of the linked list will be exactly equal to 4. So now what do? After you run this right pointer n-1 number of times, now we are going to run this left and right pointer together. We are going to run this left and right pointer together till the right pointer is reaching the end of list. Okay, so first step, second step, third step, fourth step, fifth step. It doesn't matter how many steps it takes to reach the end of the node. But the point is, once the right pointer is reaching the end of the node, of course you cannot go beyond. Once the right pointer is reaching the end of the node, you will see that the left pointer is pointing at exactly the fourth node from the right. Did you get this? It works for any n. Of course, n cannot exceed the total number of nodes in the entire list itself. Then these pointers will go out of range, right? So now that we have located, right now we have located the fourth element from the right. That is the first step in solving this problem. Okay, we will have to first of all locate the nth element from the right or from the end. So once we locate that, what are we supposed to do? The same old story where we unlink these two links and remove this node completely and establish a new link, right? So how to achieve that? So now that we have located the nth node, which is this in this particular example, so how should we remove this, unlink these two links and remove this and establish a new link? always we will have to have a pointer just before the left pointer. Let's call that one previous pointer, which is like this, blue one. Okay, let's call it a previous pointer. Okay, so naturally the previous pointer will be pointing at no node initially. Okay, originally it was here, right? So the previous pointer will be pointing at no node initially. So the previous pointer, we will have to initialize it by saying that it's pointing at none. And then as the left and the right pointer are moving one step to the right, one step at a time, even the previous pointer will be trailing behind the left pointer by maintaining a gap of 1. So we know that this is where we are going to stop when the right pointer is hitting the end of the list and the left pointer is pointing at the required node to be deleted, and the previous pointer is going to point at the node at which we are going to establish a new link, right? So let's express all of this thing down in the form of a code. Let's right away start with the meat of the code, and then later on we will add some other conditional statements in order to take care of some edge cases, right? So the main part is this. So like I told you, we will have to first of all start with both the left and the right pointer must start with the head of the node, right? So let's initialize those two variables. Left pointer and right pointer, they both are set to head of the node initially. And like I told you, we are going to first run the right pointer alone. We are going to run it towards the right n-1 times, where n is the target location from the right. Okay, so how to do it? For I in range of n-1, for I in the range of n-1, we're going to say right pointer is equal to right pointer dot next. So this is where we jump to the next node. Okay, right pointer is equal to right pointer dot next. By the end of this code, we would have moved the right pointer alone to right, towards right, n-1 times. Therefore, the length of the portion of the linked list between the left and the right pointer, including both the ends, is going to be n. Okay, so what this particular line of code is doing, I've already shown you that, but let me show you that once again. Initially, both left and right pointers are set to head. They both are pointing at head node. Now, this particular line of code is going to move this right pointer alone n-1 number of times. In this particular example, let's say 3 times. Okay, that's it. So we have just moved the right pointer only. We didn't do anything about the left pointer or the previous pointer, which we didn't even initialize yet. Okay, so now we'll get to that. We set the previous pointer as none, because of course it is initially pointing at none. So we'll set the previous pointer at none. And now, like I told you, we will have to move this entire set of 3 pointers right. We have to keep them moving right one step at a time till we hit till this right pointer is hitting the end of this linked list. But how do we know that this right pointer is hitting the end of the linked list? We know that when that particular node at which the right pointer is pointing is having no next node. So that is the condition. That is the conditional statement using which we are going to run this entire set of entire triplet of pointers, right? Okay, we'll move them back. Okay, so what is it? While right pointer dot next is not none, it means you still have space to move right. Okay, so while right pointer dot next is not none, what do? We set previous as the left pointer, because of course we want the previous pointer to be pointing in that node where the left pointer is currently pointing. That is what it means to say the previous pointer is moving right. Okay, and where do we want this left pointer to go? We want this left pointer to move right one step. That can be achieved like this. Left pointer is equal to left pointer dot next. And of course, we also want to move the right pointer one step to the right. Did you get this? We are setting previous pointer is equal to the left pointer. So we are setting previous to be equal to where L is pointing currently. And we want this left pointer to move one step right, and this right pointer also to move one step right. And it is achieved by this dot next. Okay. So by the end of this code, what would have happened? This entire set will move right. it will move right again, it moves right, it moves right again, and there it stops. Okay, so once the right pointer is reaching the end, what are we supposed to do next? We will have to delete this node, we'll do it, and we want to form a link between 5 and 7. Okay, so let me first capture this 7. How do we capture this? I call it next node. Let's refer to this as next node. That next node is clearly left pointer dot next. Okay, so I have captured this left node in this particular line, and I want to unlink this. How to unlink this? After we hop on to the next node, let's unlink. Left pointer dot next is equal to none. We'll set it to none. So that will essentially kill this particular link. We have the previous pointer. What are we supposed to do with the previous pointer? We have to make sure that the previous pointer is also no more connected to this left pointer. And how do we achieve that? Previous dot next is equal to next node, right? Previous dot next is actually supposed to give us the left pointer. So we are overwriting that particular value. Okay, so we are basically removing this link as well. So previous dot next, we want that to be the next node, which is 7. Okay, so it will remove this particular node completely from this entire linked list, and we'll be able to form this new link, right? But wait, it's not that easy. There may be some challenges here. For instance, it may happen so that the previous pointer is empty. It's null. It's null node. There is no node. It may happen so. In that case, you cannot actually write something like null dot next is equal to next node. And if you're wondering like how can this previous pointer be pointing at null, I'll give you an example. So let me go back to the original linked list. So this is our original linked list, right? Okay. So initially, all these 3 pointers were like this. Now imagine n was given to be, say, 9 instead of 4. In that case, we are supposed to delete the 9th node from the right. Again, I'm telling you, since we have the complete picture of the linked list, you know how many nodes are there. Otherwise, we have no idea. If only the head of the node is given and only that will be given, we have no idea how many nodes are there. Okay, so we will have to delete the 9th node from the end. In this particular example, it will turn out to be the very first node itself. We will have to delete the head itself. Is that clear? In this particular example, we will have to delete the head node itself. Okay, but if you follow this particular code, what will happen? We will have to run this right pointer how many times? 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we reached here. Okay, we ran this right pointer 8 times. And in the next set of codes, what are we doing? We are moving this entire triplet of pointers. We are moving them right one step at a time till the right pointer is hitting the end of the linked list. So don't you see that we have already, that right pointer has already reached the end of list. So the second part of the code will not do anything at all. It will not move this triplet of pointers because we have already, the right pointer has already reached the end of list. We can't do anything. So what are we supposed to do? We know that this is the node to be deleted. If this is the node to be deleted, this line of code is totally meaningless because previous is still none. It did not move right. It is not pointing at any node. It's none. So you cannot say none dot next is next node. Next node is 2. Fine. But you cannot say none dot next is next node. That doesn't make sense. Right? So we will have to consider the possibility that the previous can be none. We are not very sure. So how to deal with this particular situation? I'll show you. All that we have to do is to run this line of code only when previous is not none. Only then we run this, we execute this particular code. If the previous is none, then we are going to set our head as, this is our new head because the head node is the one that we are deleting. So we are going to remove this. So we are going to set our head as this particular node. And what is the name we have given for this? Next node. Okay, so we set our new head as next node and we are going to return our new head. Did you get this? we say that previous dot next is next node only when the previous is not none. When it is actually pointing at any of these nodes, only then this will make sense. If the previous did not move at all, if it is still pointing at none, in that case, we are going to remove the original head. We are going to assign this. We are going to call this our new head, and we are going to return the head. But there is another edge case we are overlooking. There is another very important edge case we are overlooking. What we discuss right now itself is one of the edge case. That is, what if you want to remove the beginning of the list, right? The middle of the list is the easiest case, right? Our line of code is going to work really well when we are removing any node in the middle of the list. Okay, so for the left end of the list, or in other words, the beginning of the list, this is what we are supposed to do. What if we are supposed to remove something from the end of the list? What are we supposed to do in a case like that? In that case, there is no such thing called as next node. It doesn't exist. You cannot just remove this and link 8 to the next node. There is no next node. In that case, all that we have to do is to just remove this and leave it as it is. Nothing else. Now, how do we know that? How do we know if the last node is the one that we are supposed to remove? And how to apply or tweak the conditions here so that it will accommodate even that situation? Let's see. Okay, so let's make room for some more code. So let me move this to the initial condition. So both the left and right pointer are pointing at the head, and the previous pointer is pointing at none. Okay, now what are we interested in? What if we have to delete the last node, or in other words, the first node from the end? Okay, what if we have to delete the first node from the end? Now, I want you to focus on this particular line of code. Do you understand that this line of code won't even get executed? Because when n is 3, we are going to move the right pointer 2 times. If when n is 7, for example, we will have to move the right pointer 6 times. Here n is 1. So we will have to move the right pointer 0 times, or in other words, we are not moving the right pointer at all. So this code will not even get executed. Okay, now what else will happen? Okay, the right pointer and left pointer are going to stay together. So the remaining part of the code will get executed. So what will happen? In the second part of this solution, what will happen? All these 3 pointers will move together, right? Remember, there is no gap between left and right pointer because the first line of codes did not even get executed. Okay, so all these 3 pointers will now move together, right? And we will stop when the right pointer reaches the end of the linked list, and even the left pointer is at the same place. Okay, end of the linked list. Okay, so what are we supposed to do in this case? We are supposed to remove only this last node, that's it. And we will have to link this, the previous node, to none. Okay, so how do we write it as code? If left pointer is equal to right pointer. Okay, that can happen if and only if n is 1. So if left pointer is equal to right pointer, what are we supposed to do? The previous pointer, we have to say the previous pointer is linked to none. But even here, there can be a trouble. Another edge case we will have to consider. What if we are given just one node? All that we have is just this single node. In that case, what will happen to these pointers? Initially, all the 3 pointers will be like this. The first line of code will not get executed. I gave you the reasons why. This time, even the second line of code will not get executed because the right pointer is it has already reached the end of the linked list. So these pointers are not at all moving. In this case, what are we supposed to do? We will have to simply remove the only existing node, that is that head node. We will have to remove that and we will have to return none. Okay, so how to code it out? So this will make sense only if the previous is not none. A similar condition we have made here. This will make sense only if the previous is not none. Otherwise, we simply have to return none itself. The only node we will have to remove and return none. Okay, so finally let's return head. Okay, it may be the new head or the same head but of the new linked list, right? Now let's go to Leetcode and type our solution. Okay, let me change it to Python 3. Fine. So what are we supposed to do? First is we set the right pointer and left pointer, both of them, to head. Then we are going to run right pointer to its right n minus 1 number of times. So rp is equal to rp dot next. Okay. And we set previous is equal to none, while this is the second part of the code where we are moving the entire triplet of pointers together one step at a time towards right. Okay. So while rp.next is not equal to none, we set previous is equal to left pointer, and we set the left pointer is equal to left pointer dot next, right pointer is equal to right pointer dot next, and next node is equal to left pointer dot next, and we are unlinking the node to be deleted by saying left pointer dot next is none. And if previous is not equal to none, we set previous dot next is equal to next node. We are forming, this is where we are forming the new link. Else, if the previous is none, then we will have to return the new head, which is the next node. We assign the next node as our new head, and then we'll return it. Okay. So this is one edge case. And what is the other edge case? If left pointer is equal to right pointer, that can happen, like I told you, it can happen only when n is 1. If the previous node is not equal to none, then we set previous node dot next is equal to none. Else, if it is already none, we just have to return none itself, because it means that there is just one node in the linked list, that is the head node, and that itself is deleted. So after all this, we return the new head of the new linked list. Let's now test run this particular code. Okay, we cleared the test case. Now let's actually run this code. Great. So we cleared all the test cases, and even in terms of time complexity and space complexity, our solution is doing pretty decently. So we'll conclude here. Thank you for watching.